Welcome, everybody. It's a pleasure to introduce Professor Haruzo Hida, better known as Har to some of his close friends in India and elsewhere, from the University of California, Los Angeles. You can say that Hida's love and passion for arithmetic competes very closely with his love and passion for India, especially Indian sweets. Many of his former students now dot the academic landscape in India. My own exposure to Hida's work began when I was supervising my second PhD student in Tata Institute. And it's always a pleasure to hear his views, not just on math and arithmetic, but in general on many other subjects. And I would encourage all of you to have a chat with him on wide-ranging topics, from Japan, his childhood in Japan, to India's contributions to number theory, to where number theory is heading, and so on. So without further ado.
I'm told that my lecture series is a little too difficult for even the professional mathematician. So why not then give a lecture a little too easy for professional mathematicians? And I can do it very well. And so it's a story of, it's a history of mathematics. And I came to Princeton when I was 27 years old. It's the late 70s, 1970s. First things I did is to go to the Ford Hall Library, where I knew actually there's a collected works of Euler. At that time, it was published up to 75 volumes. Now it's 100 something. It's a thick volume of almost 400 to 500 pages, a very big book. And it didn't exist in Japan at that time. And after a couple of days, I arrived in New York and Princeton. I went to the library to pull out that book to know what Euler did. And it is fun to read his stuff. And I just talked to something out of it. Okay, so it's a very, it's a story of history from 17th century on of number theory. And at that time, there's not many mathematicians. Or perhaps there might be many, but we only know a small number of very good ones. At that time, the tools of math is almost nothing. So to do math, you need to have a real good idea. And that requires you to be very strong. On the other hand, nowadays, you have a lot of tools, harmonic theory, Lagrange theory, Coulson-Dix algebraic geometry, whatever. You can make incremental progress. You can write a paper. I'm not against that. In this way, mathematicians survive. And this way, we are a lot of them. But still, there's not many so strong mathematicians. But so at that time, people competed. Those clever guys competed to sum up. You add up to the negative integer, starting from 1 to the m, 3 to the m, of course, this 1 over 1 to the m, and something like that. 1 to the m to the m, and further going on, you might imagine m is a positive integer. So, and this number getting smaller and smaller, so it would converge somewhere to the real number. That's fine. Oh, by the way, there's a caveat. When m is 1, it doesn't converge. It's a good exercise for perhaps high school student to show that this doesn't converge when m is 1. But so they wanted to have really the sort of formula exactly determining this number. And they compete each other in that way. I call this, following the tradition, that this is zeta of m. Okay? And so the Euler was born 1707, and died 1783 at the age of 76. Usually mathematician lives too long and don't vacate their position. And the young people are having a trouble. And he's one of them. But he did mathematics very well up to the end. And so nobody fired him. He got a position at academia at St. Petersburg, Russia. At that time, it was Prussia, the sort of Germany. And he got a position when he was 17 or 18, the offer. He's a Swiss. And so he got an offer from Catherine the First. It's not the Catherine the Great, but she's very clever. And she read the Euler's paper about shipbuilding, actually ship design, and impressed by that and offered a researcher position. Bernoulli people, Bernoulli kind of people, a lot of Bernoullis, they are professors of university teaching, but Euler doesn't teach. It's a pure research position. Perhaps the first one who got this kind of thing. And if you got it when you are 17, you would perhaps accept it. And so he walked to the, so it's from Swiss, he walked to the river Rhine and got on a ship and going north to the Germany. Oh, that's the first time he rode on the ship. He wrote a paper on the ship design, but he never on the ship. And then he goes to north to the Germany, and somewhere in the north, he started walking to the St. Petersburg. And he's a tough guy, obviously. And he started tackling this problem. Okay, his formula, he proved, is that zeta of 2 is pi square over 6. Of course, you know what the pi is. And how he gets this formula, it's fairly outrageous. So he started actually summing up negative power. So 1 plus 2 to the m, 3 to the m, not to the inverse. Oh, it doesn't converge, obviously. You are clever enough, you just don't think it works. But it sort of works. I just make a small preparation. Following to Newton, I just write as nt 1 plus t plus t to the n. Then obviously you have a t as n plus 1t. Then it's from t up to t plus snt, t plus up to t to the n and t to the n plus 1. A stupid computation, you take it off. Then then t minus, I would perhaps do it reverse. Reverse. That means 1 minus t Sn is 1 minus t to the n plus 1. Okay? So if you make t, suppose t is absolute value less than 1, then you go to infinity. So you get a geometric series, something so that I call S. 1 over 1 minus t is 1 plus t plus t squared and so on. It's converging under this assumption, right? And this one, you look at that, then you consider this, you plug in prime, say 2 to the m, or 3 to the minus m, 5 to the minus m, and so on. That means you get something 1 plus 2 to the minus m. No, yeah. 1 to the 2 to the minus m twice, and so on, plus and 1 plus 3 to the minus m plus and so on. You make a product for all primes. Then you multiplying out. Then you know from the time of Euclid that every prime is a product of every number, every positive number is uniquely product of prime numbers with given power. Therefore, you get this zeta of m. So this is so-called Euler product expansion. So that Euler invented, L is prime, and 1 minus 1 over L to the m to the minus 1. This is so-called Euler product of degree 1 because this guy is a degree 1 linear form. So this is his invention. And this kind of product is usually called Euler product. If you use 1 over some monic polynomial of degree n, it is called Euler product of degree n. And what he actually wanted to do to solve this question is that you sum up 1 over n to the minus n. This is n to the n, m positive. So it's a sum of positive power. Or why not you start from n0, and we agree that n to the 0 is just 1, then you know, it's something like you plug in 1 in t. This doesn't converge, but why not you plug in t is 1? Then you get a sum of all 1. And it obviously doesn't work. It's t is 1, you plug in 1 over 0. But he's clever enough. He considered little different power. So it's something like 1 to the m plus 2 to the m. So you have something you want. 3 to the m, something like that. And you take off twice of now even number, 2 to the 1 to the m plus 2 times 2 to the m plus 3 times 2 to the 2 times 3 times m and so on. You see, this sum, you take this term, then this is just 1 to the m minus 2 to the m plus 1 times 1. If you do this, you get 2 to the m minus 2 to the m plus 1, 2 to the m. So what you get is that 1 minus 2 to the m plus 1 zeta of minus m, if it works, right? On the other hand, this you plug in, say, you just add t to the m, and then you make it t equal 1 kind of thing. Then what you get is that t minus 2 to the m t squared plus 3 to the m t to the cube minus 4 to the m t to the 4, and so on. And the general term is minus 1 to the n plus 1, n to the m t to the n. And it goes on and make t equal 1. Okay? And this is almost same as S, but it's alternating, right? So S minus T, it will start from 1, but it has to be start with T. So you consider S of T instead of minus T, you plug in and you multiply T. Okay? That's basically gives you that, yeah, it's t over 1 plus t. Is that right? Or when m is 0, I would call a t over 1 plus t, right? This corresponds to m0, right? And this is good enough. You make these 1, you get something 1 over 2. In other words, 1 minus 2 to the m0, 1, zeta of 0 is, it is 1 over 2. That's how Euler computed this strange value. What is this? Huh? Then you divide it by this, then you get zeta 0 is actually minus 1 over 2. What is this? Okay? To include n, of course, Euler is 70 or 7. He was born, so he knows differentiation invented by Newton and Leibniz. So, everybody knows, professional mathematician knows differentiation, and perhaps even non-mathematician knows it, but I recall it, that, the formula is something d over dt, t to the n is n times t to the n minus 1. In Japan, you learn it when you are a middle school student with limit process. When I was a middle school, where I didn't go to middle school, but I knew this already. In the high school, you make a 3-variable calculus. And nowadays, Japan declined, degenerated, they do only 2 variables in high school level. And 2 to 3 different? I don't think so, but, it's something like that. Okay, so I slightly changed this. This is Ramanujan differential operator. See, something like that. You have a real number and you make an exponential map, you get a real plus, right? And you have a dx over d, or dt over d, and this is invariant in the sense that you differentiate alpha, you add something, then actually so this is, maybe I'll this way, then you get first you differentiate f and you plug in x plus alpha later, because some the differentiation commute, so it's invariant differentials. And if you bring this dx dt, it becomes Ramanujan d. This is multiplicative invariant differential form, differentiation. Whether Ramanujan knew that is invariant or not doesn't matter. He knows how to use it perfectly. And then it becomes theta t to the n is n t to the n. You make iteration, you get that sort of thing, right? So also, one more thing, mathematicians perhaps hate, but you differentiate d of g over f, then you get f squared over, you differentiate first, so the dt over df times g minus f dt dz, right? If you don't agree, you'd better go back to your home. Okay? Then, obviously that's the, for example, by applying this, we know this identity. This is just theta m times this at. Is 1. And therefore, you do this business you do this business of fraction differentiation, the denominator is 1 plus t. And by this, denominator is just 1 plus t to the, it's grown to m, 3m, and so on. Therefore, you plug in 1, it's all the time non-zero. Okay, and that's a key point of this multiplicative invariancy. And so you can write this as a denominator of t and the numerator of t. And by computation, for example, d1 of t is 1 plus t in square. The numerator 1 of t is just t. And this tells you that 1 minus 2 square zeta minus 1 is, you plug in, this is 1 plus 1 square, so it's square outside, I'm sorry, is 4 over 1. And therefore, zeta minus 1 is minus 1 over 12. It's negative. You add up all squares, integers, you get negative number. And Euler thought this is funny. And so he started studying this very seriously. And he found some extraordinary formula that tells you this is when he was aged 28, after 10 years in St. Petersburg. He wrote so many papers. He computed so many things in, you don't have this kind of electric light. He did it under the rather dark place. And he lost by cataract the right eye eyesight when he was 28. So he becomes cyclope. And what he found is that zeta to m, now m positive all the time, equal minus 1 to the m, 2 to m minus 1 factorial, and 2 pi 2 to the m zeta 1 minus 2m. And you plug in m to be 1, if this formula, you get this formula that pi square over 6. Actually, he stated this, and he didn't prove it. Although he did give a proof for small m. M is 1 okay, 2 is okay. I don't remember for some, perhaps up to 8 or something like that. And perhaps out of this, he guessed it. But nobody knows whether he had a real proof of this or not. And later, math historian wanted to know whether Euler could have done that or not. And if you allow all the formulas he invented towards the end of his life, he died 76, and he's active towards the real very end. And then you can actually prove it. So he might have had this. And next thing is that Riemann proved this. First, he made a complex holomorphic function if it can be extended. This is okay only for positive m, and you replace m to some complex number now. Then the real part s is bigger than 1. It converges, you get a holomorphic function of s. And if you can extend it towards the, so you have a right side well-defined object, but you go left, if you could extend it to the meromorphic function, that's unique. That's what Riemann proved. And he proved this formula for entire S. it is something like that. 2 gamma s cosine pi s over 2 pi s zeta 1 minus s. This is a reflection. S goes to 1 minus s, and we call it functional equation. And this number is sometimes we call it weight. So this Riemann zeta function we call, it should be Euler's zeta function, but it's weight 1. Degree 1, weight 1. Okay? And gamma s is a gamma function of Euler. This is also Euler. If you plug in integer m, you get a m minus 1 factorial, and it's a complex analytic meromorphic function of entire plane. So it's exactly this. So Euler might have known everything appeared here, Euler knew. And even its Taylor expansion he knew. And you use Taylor expansion, you get actually this. So it's something, kind of mystery, but that things goes. Okay, so this is the story of Euler. I spent 30 minutes. For next 30 minutes, I a little bit explain the p-adic number. So this I read in the IAS Princeton Institute library. And Andre Weil, perhaps mathematician knows, great mathematician, was there. And he is also reading Euler. He is perhaps a unique mathematician who read most of Euler, at least math papers. And I read from 9 to 9:30. Then he comes, he kicked me out, took my book, and then he read to the about 11:30 or something. And I continue to do that. It's every Tuesday and Thursday. I also come 9. He come 9:30. And it's fun to meet him. I didn't really knew that at that time, at the beginning, that is Andre Weil. So I was very rude to him. Because I was so confident. I was clever, I thought. Okay, so because the number in the numeral system is something like that. If you write, yeah, if you write some number, alpha 0, alpha 1, alpha 2, something, this is just means alpha 0 is integer, alpha I between integer, and alpha I is between 0 and 9. So plus alpha 1, 1 over 10, plus alpha 2, 1 over 10 square. This is Indian numeral system. Indian mathematician invented in the 6th century or 5th century or something like that. Okay, so that basically comes from, you have two vectors, x and y, you add up by parallel two flow, you get x plus 1. So the length, you intuitively know going to direct is better than going with this kind of detour, right? It's not a proof, but it tells you that x plus 1. This is a triangle inequality. And pick a prime. P, this is about Kummer. He is something oh, I might have lost some papers, stupid. That's okay. Kummer is most of 19th century. He lived up to 80 something and born very early of 18th, 19th century. Notorious mathematician, very clever, having a lot of ideas. But he's so clever. He hates most of mathematicians because looks stupid. he criticized people, and he has so many ideas. So like me, he made a lot of errors. I instantaneously admit my error. He didn't. So he was mostly quite hated by the people or mathematicians. And his collected works, about 2-volume, 700-page kind of thing, was not published after his death because anybody is against to it. And Andreev published it in 1976. And because he wrote in the preface that it's quite unfair considering Kummer's talent. And I think they also read most of Kummer's paper, I believe. And okay, so if you write integer to p to the some power and n prime so that p doesn't divide n prime to n, then you define p-adic absolute value to the 1 over p vn. And this is quite easy. Actually, you can do this for fractions. You do this for denominator and numerator and put it denominator and numerator. And so it has this absolute value for any fractions. And x plus yp is less than max, bigger than the 2. That is, of course, less than xp plus yp. And this stuff is just you complete, you add all the limit of like that and to get real numbers. And that's how Indian mathematicians did. But you can do this for this one. That's Kummer's idea. So you get Q. If you use usual absolute value, you get a real number. You get Q of this p-adic guy, you get a QP. Okay? For simplicity hereafter, I suppose P is the odd prime. 2 is the king of prime, it comes first. It's all the time resist anything. So that's something I have some trouble. All right. So you remember Fermat's little theorem. If you have integer a prime to p, and then you raise power p minus 1, that is congruent to 1 modulo p. This is Fermat's little theorem, not the last theorem. Okay? And this just means a p minus 1 is divisible by p. And this congruence symbol behaves just like equality. You make a left-hand side product, right also becomes this product. It's something like that. And it's amazing, Euler is so clever, but he found generalization to p power only when he was quite old. And Euler's theorem is that same notation, a p to the l minus p to the l minus 1 is congruent to 1 modulo p to the l. This just means if m and n prime is congruent to p to the l minus p to the l minus 1, then m to the p to the l is congruent to m to the p to the m prime p to the l, something like that. Mod p to the l, right? Because the difference is this guy. You raise the power, you get 1. So you get same thing you get, right? In other words, if m minus n prime p is less than, say, 1 over p to the l minus 1, then m p to the l is congruent to m p to m prime p to the l difference. is less than 1 over p to the L. Okay, but this is valid for integer prime to p only. Huh? Of course, if p is divisible by p, you raise the power, it is highly divisible by p, so you don't get anything. And this is now the p-adic story that I just take bt to be 80 minus 80 to the p. This just remove those, but p doesn't divide those not prime to p of minus t to the n, and do the same business as Euler did. Then you find, because these two things there, so you have just defined zeta m to be definition d to the m bt over d to the m very theta. No, zp. Then you get 1 minus 2 to the m plus 1. This is Euler's factor. And minus p to the m coming from this difference. And zeta to the minus m. The point here is that, formally at least, if m and m prime is close 1 over p to the l minus 1, then zeta m minus zeta m prime is further close. So at least, because there's a strange p minus 1 factor showing up from the Fermat-Rayleigh theorem, at least for A in p minus for m in A, but you just allow only those moving this, and you consider m going to Zm, and this is values in QP, and this is in Z, but Z is also in QP, right? Because you complete it. But this is a continuous function on this metric. So it extends as Riemann did, that I just fix 1A, a fix. And then this guy is actually densely populated here because this is prime to P. And therefore, you get a S in ZP, okay, actually ZP. Those of this is a closure of integers inside QP, because this is QP, but this is only integers. To element S2, you get ZS inside QP. Okay? This is so-called Kubota-Leopold p-adic function. If you plug in this integer, positive integer m, you recover this Euler's original value. And this was done by Kubota-Leopold, 1964. Actually, Kummer basically proved this 1850, Kummer. And Kubota-Leopold (1964). Whether these two guys knew Kummer or not is not clear, because collected work is not published in this time. So they didn't perhaps know Kummer's results, actually. But anyway, something like that. And it's therefore, Riemann extended to all complex number. These people extended to all the p p-adic integers. And you have a same value. And it's a continuous function at that time. But actually, this is analytic. This is a has a power series expansion, converges over all ZP. And this was Iwasawa's result. Iwasawa's result, 1969, I think. Okay. I have still 20 minutes, so I want to go to Ramanujan. Perhaps you feel that if you write a nice paper, present day, you are not sure after 10 years, any mathematician remember it or not. Usually the paper dies in 3-4 years. But I'm talking about this paper of Euler 300 years ago. It's not forgotten. And these guys are also very old hunch. And you need to write once in a lifetime that kind of paper. And then you are a great mathematician. Once is perhaps enough. Although Andre Weil told me that, that's what Andre Weil told me when I was reading Euler. And you need to have 3. Yeah. And well, whether I had 3 or not, I'm not sure. But anyway, that's what he mentioned. Okay? So, here's a Ramanujan. You know Ramanujan well, at least in a postage stamp or something. India produced 3 different postage stamps of his. It's a pride of India, I believe, but he died very young, of 32 or something. 1887 to 1920. And he studied this Ramanujan's delta function. Sometimes I write delta 12. You will see the reason soon. And it's 1 to infinity of 1 minus q to the n to 24. And you multiply out tau n, qn. Tau n is, of course, integers. Yeah? I think Ramanujan computed about 100 terms of tau n. And I knew that when I was a senior year of undergraduate, and I started computing it. Oh, second day I tired of it. I had a girlfriend. She's a computer programmer, computer scientist, perhaps first Japanese computer scientist. And she was a professor at Kyoto University. I was an undergraduate student. Why not ask her? And she computed just next day. At that time, the portable computer, they say, is about the big fridge size. And she's quite good at that. And the Ramanujan conjectures 1916, you just make L m delta 12 to be you twist tau n, and it's 1 to infinity. If you want, you can plug in s also, but this kind of wave function he made. And he conjectured that this has an Euler product of degree 2. Inverse. So this is a 1 minus tau n x plus tau n, no tau n, L to the 11 x squared. So this is a Euler product of degree 2. Ramanujan is perhaps the first guy who saw the Euler product of degree 2. And particularly, this implies that tau prime p and tau prime q, you make a product, you get a tau prime pq, p different primes. So my girlfriend, currently my wife, computed this. So I checked by that. I told her that it's correct because of this is true. She said, I knew that. I once computed, I saw it, then I found this law. So she's clever. And I was quite surprised. Anyway, this was proven in 1917 by Model. Model's theorem. Okay, so this delta has a lot of incarnations. For example, if you replace q by exponential 2 pi square root of minus 1z or something, you get a modular form of weight 12. So that's why I call it delta 12. And they Shimura found in 1952. Now Shimura. He lived most of the 20th century, proved that. So you remember, zeta 2m divided by basically 2 pi to the 2m, and you divide zeta 2m prime over 2 pi to the 2m prime. This is a rational number of fractions. That's Euler's theorem basically tells you. And Shimura proved that Lm delta, you divide 2 pi square root of minus 1 to the m, and Lm prime delta 2 pi square root of minus 1 minus 1. I'm sorry. M prime minus 1 is a rational number. Similar, however, only m allowed is 12. And actually, m has to be congruent to m prime modulo 2. Oh, disappointment. And then later, so I can't make this the m because you need an infinitely m to have this kind of continuation. You have about 12, about 6 of them, no way out. And so, but slightly later, 1972, Russian mathematician Manin, UI Manin, found Manin constant, so to speak, Manin period, perhaps omega plus minus delta. It's a complex number, canonically defined, that 2 pi I m minus 1 omega plus or minus, it's a 2 of them. And this depends on this parity of m, modulo 2 thing. So you need to choose either one. And this is Lm delta. So Q. Actually, you have 2 transcendent, perhaps, pi and this guy. It's an Euler product of degree 2. Huh? And okay, but still you can do. So I need to extend some delta. At that time, I started reading Euler, it was age 27, and I realized that Euler found this kind of thing 128. I need to find something. And so I actually found something. I actually found, when I was 28, I found that if tau is probably your prime, it is not congruent to 0 modulo p. This is kind of I needed. Then I found a unique modular form I call delta k. That is n is 1 to infinity tau of kn q to the n weight k. And it has, you make L m delta k, then it is the Euler product of degree 2. K is 12, it is 11, right? The k minus 1 comes out. Tau k L, L to the minus. And you see, this ZP intersected integer, no, Q, is actually just a fraction, entire fraction. The P doesn't divide the denominator. Why not you take ZP intersected all algebraic numbers? So this I call it V, and this I call it V bar. ZP contains a huge amount of algebraic number, which is the root of the rational coefficient polynomials. And this is a big ring, but still it is in ZP. You have alpha, then you have its metric. It is in Q, right? And this Shimura's theorem, Manin's theorem, works well. So it's the same thing here, but I put K here, and then I put a K here. Then it's something like that. Now it becomes K. And this one, I need to put K here, and it's K. Now Kn is the coefficient of this cusp form I found, delta K, tau of weight K. And this tau of weight K resides in V bar. So, okay. And so you know that this is, I have now a lot of numbers. I have two things, K and M. And the relation is 0, M, K, and also parity condition. Mod 2 is something minus 1, so the parity condition. It's infinite remaining. I can do the same game now. And actually, in 1994, independently Meza and Kitagawa, it's my student, Kitagawa is, proved that there's a K I write, but this is MK. It is in ZP twice. Okay? 2 QP analytic function. Maybe I would say ST. And this is ST. Analytic function such that zeta MK is this basically, you see, in the case of original Z, I need to remove one Euler factor, 1 minus p to the m kind, that kind of maneuver I need to do. But anyway, basically this value is, this is V. Condition tau p, yeah, I have assumption tau p not congruent modulo. So I have a condition, this condition. Yeah. So this condition, still have time? Yeah, I have 5 minutes. this condition fails sometime. And so actually, when I was 28, what I found under this condition is that k goes to tau k n, given n, is a continuous function of k on ZP. And actually later I proved it was analytic, but at that time I only know this. And so tau p fails the condition it is modulo p occurs if p is 2, 3, 5, 7, then 11 gone, 13, 2, 4, 11, and then big 7, 7, 5, 8, 3, 3, 7, 6, 3, 3. Perhaps there will be infinitely many, but nobody knows. Such p bigger than 10 to the 10 yet. And it should be very sporadic, but there could be infinitely many. And this is basically what I wanted to say. But this type of two, so it's a degree 2 Euler product. You have a 2 variable L function, 2 transcendental factors, and now you have a theory of degree n L function, of course, and all this kind of things is analytic. And this kind of, so it's something like that. You start with delta 12, so 12. So say p is 11. P is 11. Then you can down to 2, the difference is p minus 1. Then you have a 22, you have a delta 22, and they are congruent to mod p. Okay. If you, so starting from 12, then if you, so 11 times 11 minus 1 is, you can compute 110. So if you go down, then you get into suppose 0 and negative, no modular form for negative type. But on the other hand, you can climb up 122, and it goes, then delta 12, delta 122 is congruent to modulo 11 squared, something like that. And you get a lot of modular form in this way. Okay, so thank you for listening to me.
Thank you very much for a very inspiring, very entertaining and stimulating lecture. Questions? If I'll maybe start with one. So these analytic functions of 2 variables, if I understood right?
Yeah.
Do they have an analog of a reflection kind of?
No, for p-adic case, whether there's a reflection or not is not yet clear. So the functional equation, this complex L function has a functional equation. L S delta K as a functional equation K, S goes to K minus S. So this you can take as a definition of weight. But for p-adic things, even original dot Z, Kubota Leopold Kummer, seems not having real functional equation. But this one might have, but I'm not totally sure.
What is the field that you get if you adjoin all these tau k n's, fix the k, tau k n's to, so what is the rationality field?
K climb up this way. This is K. So K and
Yeah, take one of those k's, fix it.
then tau K n is congruent to tau is 22, tau original is congruent to modulo 11. In this case, it's modulo 11 squared, something like Riemann zeta function. You raise the power to the m to the p to the l type of thing. Okay? Yeah.
Yeah, so what is
So
that?
Sure.
It's a very concrete example. So what would be that number field is what I was asking. So
number field showing up is that V bar. So I later proved that all you fix one prime L, you add all tau k, say one prime L, k running, and this is as infinite degree over Q. So it grows very fast. And if you admit Maeda's conjecture, then the degree of this guy is dimension of weight k cos form. Okay. And Maeda's conjecture not yet proven. So
If you fix a k, then do you have,
I started from 12,
right? Okay.
then moving k.
Okay, no, but suppose you fix a k, then do you have model-like properties for the coefficients?
Oh, yeah, sure. You start from something at weight k, then you can move around in the same way.
And suppose you vary k, then you gave one example of congruences here.
So you know,
Is there a general formula?
so general formula is that you start from k node, then all k node plus p minus 1z, positive guy, has, for that integer k, you have a weight k form with this property, starting with fk0, and then you climb up similarly to that kind of way. And it's the same thing. That I knew at that time. But only continuity I know at that time. I proved analyticity and so on later, a couple of years later.
Other questions? If not, let's thank Professor Hida again for a very nice